The next topic that we want to talk about are velocities and accelerations. There's a distinction that we're going to have to make, so let's go back and think about what we did in the first semester. If you represent t as being time and x of t as the position of some object at time t, then the velocity was given by the derivative of x with respect to t, and the acceleration was the derivative of the velocity, which would be the second derivative of x with respect to t. The v and the a in this case are numerical quantities. They could be positive, negative, or zero. As a very simple example, think of the x-coordinate as being one more than whatever the time value is. dx dt would be the constant 1. The second derivative of x would be 0. The acceleration is 0. The speed is the absolute value of dx dt, which is 1. This is true no matter what t values you are looking at, so we would say that the object is moving at a constant speed in this case. Now, as we pass to Calculus 3, we're thinking of positions of things as being described as vector-valued functions. So let's be explicit here and say that r of t is the x-coordinate at time t times the I vector plus the y-coordinate at times t times the j vector. We're going to do just as we did in Calculus 1, except we're dealing with vectors now. The velocity vector, v, is the derivative of the position vector, so it's dx dt I plus dy dt j. The acceleration vector is the derivative of the velocity vector with respect to time. The derivative of v with respect to t will have in its first component the second derivative of x, and in its second component the second derivative of y. We need to make a distinction here. Velocity is a vector. Speed is the magnitude of this vector. If we don't keep these two ideas distinct in our minds, things could get pretty confused. I want to return briefly to the examples that we were talking about when we were discussing smoothness. I want to think of r equals t times I plus t times j as opposed to r equals t cubed I plus t cubed j. In both of these formulas, the x and the y coordinate are equal to each other. So in both of these setups that we're looking at here, we're talking about traveling along the straight line y equal x. If I'm just interested in the geometrical points that we're looking at, there is no important difference between these two things. But if I'm thinking about position and time, there is. The velocity vector in the first one is the constant vector, I plus j. The magnitude of that is radical 2. The acceleration would be the derivative of the velocity vector. The velocity vector doesn't actually have any t variable in it, so the acceleration is 0. This situation, if t is time and r represents position, represents unaccelerated motion. On the other hand, in the second one, the velocity vector is going to be 3t squared I plus 3t squared j. This points along the same direction as I plus j when it has a direction. The speed, though, depends on the time. The acceleration vector is 6ti plus 6tj. This setup represents accelerated motion along the line y equal x. Let's look at the vector-valued function r of t equals t squared I plus t cubed j plus t to the fourth power k, I'd like to find the velocity vector, the speed, the acceleration vector at the time where t equals 1. Also, I'd like to find equations for the tangent line. Firstly, at t equal 1, x will be 1 squared, y will be 1 cubed, and z will be 1 to the fourth. So the point on the graph of the tangent line that I know is 1, 1, 1. The velocity vector in general is the derivative of the position vector, 2ti, 3t squared j, 4t cubed k, and the acceleration vector in general is the derivative of that, 2i plus 6tj plus 12 times t squared. I'm now ready to evaluate these quantities at t equals 1. Setting t equals to 1, I find that the velocity vector is 2i plus 3j plus 4k. The acceleration vector is 2i plus 6j plus 12k. The speed at the moment when t is 1 is the magnitude of the velocity vector at t equal 1, which is the radical of 2 squared plus 3 squared plus 4 squared. If I want to have equations for the tangent line at the point 1, 1, 1, what I need to write down is x, y, and z. Then over on the right-hand side, I'll have the x, y, and z coordinates of the known point that I've got. I'll have the components of the direction. That would be the velocity vector in this case. And I have a certain amount of freedom here. I need to fill in these three blanks with the same quantity, and I really don't care what the quantity is as long as it takes on all real values. So, for example, I could fill those blanks in with t. That seems like the simplest thing to do, although it does run into a naming conflict. At the point where t is 0 in this set of formulas, you get the point 1, 1, 1, which corresponds to t equal 1 in the original formula. That's a point of possible confusion. It probably would be better to use some other letter here. You could, for instance, fill in the blank with s plus 1 in all three places, and then simplify the resulting expression. This would be an equally valid way to describe the tangent line. Or, if you had some particular reason for doing so, you could fill in the blank with t cubed all the way down. It doesn't make any difference how you do the parameter exactly, as long as the quantity that you fill the blank in takes on all possible real values. I want to think about b and omega being positive constants. I want to consider the vector-valued function in the plane r equals b cosine omega ti plus b sine omega tj. Thinking of this coordinate-wise, x would be b times cosine omega t, y would be b times sine omega t, and if you calculate what x squared plus y squared is, it turns out that x squared plus y squared is b squared. I'm going to take the b and the omega to be positive. In this vector-valued function, the graph is a circle with radius b centered at the origin. The number omega, from a geometrical point of view, has nothing to do with anything. If I'm thinking about an object actually moving around in the circle, though, the omega is the angular velocity. It's how many radians per second the object is traveling around the origin. I'd like to figure out the velocity vector, the speed, and then if we think it's necessary, we'll calculate the acceleration vector as well. The derivative of omega cosine t, the derivative of cosine omega t is negative sine omega t times derivative of omega t, which is where this extra factor of omega comes from. Likewise, the derivative of sine omega t is b times omega times cosine omega t. When we calculate the speed, we take the components of the velocity vector, square them, add them up, and take the principal square root of the result. After a little bit of manipulating, though, we see that we can use our familiar trig formula. Cosine squared plus sine squared is 1. The speed is radical b squared omega squared. Both b and omega are taken to be positive here, so that radical is just b times omega. The speed is a constant. It's the radius of the circle times the angular velocity. The speed is a constant. Do we even need to calculate the acceleration vector? After all, the speed is never changing. The speed is a constant. Does that mean the acceleration vector is the zero vector? If we take the derivative of the velocity vector, we pick up extra factors of omega again. The acceleration vector turns out to be negative b omega squared cosine omega t I minus b omega squared sine omega t j. That is definitely not the zero vector. Even though the speed is a constant, the acceleration is not. This is why we have to be careful about our language here. The reason for this is the acceleration vector is the rate of change of the velocity vector, not the magnitude of the velocity vector. As our object moves around in the circle, the length of the velocity vector, which is the speed, never changes, but its direction does. When the object is here, the tangent direction is in that direction, but here, that way, that way, that way. A vector can change either by changing its magnitude or changing its direction, or just one or the other, or even both. I want to figure out the magnitude of the acceleration felt by an object moving around in a circle of radius b with angular velocity omega. Take the components of the acceleration vector, square them, add them up, do the cosine squared plus sine squared thing, and radical b squared omega to the fourth is b times omega squared, since b and omega are both positive. The magnitude of the acceleration is b times omega squared, but the velocity has magnitude, that is to say, the speed is b times omega. So if I want to write this in something that I can relate to the physics and geometry of the situation, I'll take b omega squared and write it as b squared omega squared over b. This is the square of b omega divided by b. This would be speed squared divided by the radius. If you have an object moving in a circle with a certain radius, b, with a constant speed, the acceleration is going to have magnitude speed squared divided by the radius. In logic, there are a number of classical errors, one of which is called the argument by incredulity, which means basically you say, I don't believe that that could be right, so I must be right, which of course is a logical error. I want to take this opportunity, having figured out speed squared over radius, to make fun of the flat Earth people, because they deserve it. A commonly heard argument is this: the rotation of the Earth near the equator is supposed to be very fast, thousands of miles per hour even. Why don't people get flung out into space if they're going that fast? Near the surface of the Earth, objects are attracted towards the center of the Earth, and in free fall would experience an acceleration of about 9.8 meters per second squared. On the other hand, if you are going around in a circle, there is a certain outward flinging tendency. The magnitude of that outward acceleration is speed squared divided by the radius. So let's figure out how big that is. The speed is the distance. The Earth goes around one complete revolution in 24 hours. So 2 pi times the radius is how far a point on the Earth travels during one revolution. One day has 24 hours in it, each one of which has 60 minutes, each one of which has 60 seconds. A point on the equator of the Earth is moving about 465 meters per second relative to the center of the Earth. So near the surface of the Earth, there's a tendency of 9.8 meters per second magnitude of acceleration to fall downwards. After doing the arithmetic, it turns out that speed squared divided by radius is about 0.03385. This is why people on the equator are not flung off into space. The downward acceleration due to gravity is much bigger than this circle-induced acceleration. I want to split the section on velocity and acceleration up into 2 chunks. This is the first chunk. We'll do the second chunk tomorrow. Hopefully everyone is staying warm, being safe, and I'll talk to you again soon.